Let us continue with chapter 9 today. These are the answers for today's questions. Questions 1. The work function for platinum is 6.35 eV. An ultraviolet light of wavelength 150 nanometer is incident on the clean surface of a platinum. What is the photon energy of the ultraviolet light in eV? Discuss whether these photons will eject electrons from platinum. What is the maximum kinetic energy of the ejected photoelectrons? Determine the stopping voltage required to arrest the current of photoelectrons. Since the questions involve the ejections of an electron, now let us analyze the question first. See, the information given belongs to which stage of the questions. So when it comes to the ejections of photoelectron, this is the process. You have an incident light, it hits a metal surface. Inside the metal surface, there's a free electron. And this free electron will be knocked out and becomes photoelectron. So questions give you the work functions and also the wavelength of incident light. So now you have the information for this incident light, which is a lambda, and the work functions which belongs to free electrons inside the metals. And according to the question, it is asking for the energy of ultraviolet, which is the incident light. So it belongs to this stage. So which means questions A is going to focus on the incident light, which is this part of the process. To determine the photon energy, which is the energy of the incident light, so let's apply equations E equals to hc over lambda. Now, recall the information that you have in the diagram. You are given the wavelength of the incident light. Therefore, you can calculate the photon energy by using this equation straight away. So substitute the values into the equations. You now have E equals to 1.33 times 10 to the power of negative 18 joule. But that is not the end of these questions yet, because the question is asking for the answer in EV. So 1 EV is equals to 1.6 times 10 to the power of negative 19 joule. So now you can do unit conversions and eventually you will obtain E equals to 8.31 EV. Questions B asks you to determine whether electron will be ejected from the surface. So how are we going to tell whether electron can be ejected or not? So we can do the comparisons between the photon energy and work function. So given work functions equals to 6.35 E, and from questions A, you obtain incident light energy, it is equals to 8.31 eV. So when you compare these two values, you will see that photoelectron can be ejected. Why? Because the incident light energy is larger than the work function. Question C asks you to determine the maximum kinetic energy in photoelectron. So now let us go back to the diagram. Given information about the incident light wavelength, and then we have the work function, which is the energy needed to break free the electron. And then photoelectron belongs to the last stage of the process. And this question is asking for the kinetic energy inside photoelectron, which means we want the information in this final stage. But if you look at the diagram, we don't have any information about the photoelectron. So now let us determine the kinetic energy by using the equations E equals to K max plus W naught. Because we have the information about the incident light, we have the work functions. Therefore, we can apply these equations to determine the K max. So substitute the values in the equations and you will then obtain K max equals to 1.96 eV. Question D is asking for the stopping voltage. So the equations that can be used to determine the stopping voltage is K max equals to EVS. From previous questions, we have K max equals to 1.96 eV. So substitute the values into the equations. You will then obtain Vs equals to 1.96 volt. Questions 2. The work functions of tin is 7.1 times 10 to the power of negative 19 joule. Calculate the minimum frequency of ultraviolet radiation required for photoelectric emissions from tin. Questions B. Find the frequency of ultraviolet radiation needed for the emitted electron to have a maximum kinetic energy of 2.5 times 10 to the power of negative 19 joule. To determine the minimum frequency required, first you must understand what does it mean by minimum frequencies. Minimum frequency, it doesn't represent the frequency of incident light. It is a threshold frequency, which needs to be calculated by using the work function. So given W naught equals to HF naught, substitute the values into the equations, you will then obtain minimum frequency, which is a threshold frequency, equals to 1.07 times 10 to the power of 15 Hertz. Questions B is asking for the frequency of ultraviolet radiation. Now this question is asking for the frequency of the light. So let us analyze the questions again by using this diagram. So if you look at this diagram, again, we have incident light, which is the ultraviolet radiation. It hits a metal surface and it then knocks out this free electron and gives you the photoelectron. So according to the questions, you are given work function equals to 7.1 times 10 to the power of negative 19 joule. And it tells you the photoelectron must carry an energy that is equals to 2.5 times 10 to the power of negative 19 joule. However, we are not given any information about the incident light. But we can calculate the photon energy by using equation E equals to K max plus W naught. Once you have this photon energy, you can then use it to calculate the frequency of ultraviolet radiation. So now let us substitute K max and W naught in equations. You will then obtain E equals to 9 times 10 to the negative 19 joule. Now that you have the photon energy, let's apply the equations E equals to HF. Substitute the values into the equation. You will then obtain F equals to 1.45 times 10 to the power of 15 Hertz. Questions 3. In a photoelectric experiment, the cathode of a photocell is exposed separately to electromagnetic radiation of frequency 6.9 times 10 to the power of 14 Hertz and 11.8 times 10 to the power of 14 Hertz. The maximum kinetic energy of photoelectrons is 7.9 times 10 to the power of negative 20 joule and 4 times 10 to the power of negative 19 joule. Sketch a graph of K max against F. On the graph, mark the values of frequency and maximum kinetic energy mentioned above. Questions B. Use a graph sketch in questions A. Determines the values for the Planck constant and the work functions of the cathode. C. If a metal with a lower work function was used in the experiment, draw a line to represent the possible variations of K max with F on the graph sketch in questions A. Questions A wants a graph of K max against F. So how are we going to solve this type of questions? It is always a good idea to start from the general equations E equals to K max plus W naught. So since the questions want the K max as a y-axis, so let us rearrange the equations. So now we have K max equals to E minus W naught. However, we don't have F in these equations. So what can we do? Now let us try to expand the equations. So if you expand the equations, now you have K max equals to HF minus W naught. let us check whether we got the right equations by comparing these equations with y equals to mx plus c. So by comparisons, we now have k max as our y-axis and f as our x-axis. So let us start the sketching now. So according to the questions, we have k max as the y-axis and f as the x-axis. So we are given 4 values in the questions. Let us put it in our graph. So we have 0.79 and 4 along the y-axis, 6.9 and 11.8 along the x-axis. And then according to the equations derived, we have work function located at the negative y-axis. Now that we have everything, let us sketch the graph. So you have a straight line graph where when x equals to 6.9, the y is equals to 0.79. When x equals to 11.8, your y is equals to 4.0. So that is the answer for questions A. Question B asks you to determine the Planck constant from the graph. Remember, when you have this type of questions, you cannot simply give the answer from the list of constant. So what are you going to do? Now let us go back to the equations that you derived from previous question. So K max equals to HF minus W naught. Once again, compare with Y equals to mx plus C. You will see that the Planck constant is the gradient of the graph. So now that you know the Planck constant is coming from the gradient of the graph, let us go back to the graph again. So now we have this graph with 2 points given, which is when x equals to 6.9, y equals to 0.79, and when x equals to 11.8, y equals to 4.0. So what are we going to do? So h equals to m, which is a gradient, and we know gradient is equals to y2 minus y1 over x2 minus x1. You have 2 points, means that now you have y1, y2, x1, and x2. So substitute the values in the equations, you will then obtain h equals to 6.55 times 10 to the power of negative 34 joule second. So when it comes to substitution, remember to include the power, which is times 10 to the power of negative 19 for y and times 10 to the power of 14 for x. Second part of questions B asking for the work function. So can we get a work function straight away from the graph? Let's see. Well, apparently no. Why? Because there's no information given about the y-intercept. So what can we do? You can choose either one point in the graph and then substitute it into the equations to obtain the function. So W equals to HF minus K max. Now let's assume I'm going to take the x as a 6.9 and y equals to 0.79. So substitute these two values into the equations. Then I will obtain W naught equals to 3.73 times 10 to the power of negative 19 joule. Now, if you are going to take x as 11.8, then you must take y as 4. If you substitute this value into the equation, you will still obtain the same answer, which is 3.73 times 10 to the power of negative 19 joule. Once again, question C is asking for a graph of K max against F. But now it asks you what happens if a method with lower work function is used. So according to the equations that we derived from previous questions, W naught equals to HF minus K max. And it wants you to sketch it in the graph from questions A. So let us look at the diagram again from questions A. So this is a graph from questions A. And how are we going to sketch the graph? Well, let's assume K max is equals to 0. So if K max is equals to 0, then when work function decrease, frequency will decrease. So these two values would tell us where is our graph when it passes through y-intercept and x-intercept. So if W naught decrease, F node decrease. It means the new graph would be located on the left-hand side of the original graph. So this blue color line is the answer for questions C. So that's all for today. I will see you all again tomorrow.